All right, yeah. Hi, everyone. Thanks for coming today. Today we're very happy to have Shahin Jabbari as our speaker. Shahin is an assistant professor at Drexel right now. Before this, he was a postdoc at Harvard and he was a PhD student at Penn. He's done a lot of research in the space of machine learning and game theory with a focus on like the societal aspects of algorithmic decision making and fairness and those kinds of issues. And today he's going to tell us about his work on post-hoc explanations, unification, robustness, and disagreements. Yeah, take it away, Shahin. It's all yours.
Yeah, thank you. I always enjoyed this talk, so happy to give a talk this seminar. Today I'm going to talk about post-hoc explanations, and this is joint work with a lot of people, combination of two papers. I kind of lost track of where everybody went, but when we started this project, Chirag was a postdoc at Harvard, Sushant was a master's student at Waterloo, Tessa was a PhD student at Harvard, Alex was an undergrad at MIT, Satya was a PhD student at Harvard, Hima still at Harvard, Javin was an undergrad in Harvard, and Suhini was a PhD student, and Stephen is in Carnegie Mellon. The joint work with a lot of people. So today, I'm just going to talk about a little bit of kind of like a background that what sort of like we mean by explainable machine learning, and then I'm going to talk about two different threads. So let me just dive in. So I guess for this audience, it's just really there is no need to motivate that we're using machine learning in many settings today that traditionally we use humans, and kind of like one of the major challenges is how to basically make humans trust these machine learning models. And kind of like one way that you can approach this problem is you want to kind of like make systems that are explainable. So basically these explanation can be used as a measure of trust. This explanation can be used as a measure of like kind of like audit your model. This explanation can be used as a measure of kind of like measuring different properties of your system. And in this talk, I'm just going to talk about a specific class of these explanation that is called post-hoc explanation. So sort of the idea here is you have this complex model. It can be a deep neural network, and you are going to explain the decision of the model at a very specific input. So for example, in the example that you see, there is a patient, it has a bunch of attributes, and the model has predicted flu. So our goal here is to just explain why the model is predicting flu for this specific patient. So if there's a new patient, we have to kind of give an alternate explanation. And specifically, today, I'm just going to talk about a type of post-hoc explanation that is called feature attribution method. So in feature attribution method, you just want to highlight the features that are important in the decision-making of the model and to what extent. So for example, in the example that you see on the slides about the flu, kind of the explanation that we give from the model for this patient is because this patient sneezes and has headache, but there is no fatigue, the prediction is going to be flu. And kind of like you're going to pick a subset of features, and you kind of like also want to specify how important these features are in making the decision, kind of like either positively or negatively. So let me formalize the setting. So here today, I'm assuming that there is a complex function f, and this function is available to us. It's defined over a continuous space in RD. And for the purpose of this talk, I'm just going to assume the output of this function is continuous. So you can kind of think about in a classification setting, maybe the function does not give you 0 ones exactly. It gives you the probability that the label is 1. So as I said, we want to do post-hoc explanation. So we want to explain the decision of the function f at just the specific point x. Okay, so let me just give you some background of some of the explanatory techniques that have been developed over the past 5 or 6 years. So these post-hoc explanations usually fall into two major categories. One is called gradient-based explanation, and the other one is perturbation-based. I'll talk about each of them shortly. But for the gradient-based explanation, you can kind of think about the simplest version, which is called the vanilla gradient. Your explanation is just the gradient of the function at the point that you want to explain. And kind of the motivation for that, especially in a domain like image classification, is sort of like you want to highlight the specific pictures that are important for your model to make the decision of what is actually in the image. So for example, you see that if we do just the vanilla gradient, this is the sort of explanation that you get for the picture that corresponds to the drilling platform. So the problem with the vanilla gradient is gradients are like sort of like the result that you get is very noisy. So one way of kind of dealing with that is instead of just computing the gradient at the specific point that you want to explain, you sample a bunch of points nearby to the point you want to explain, you compute the gradient for each of them, and you kind of average them out. So kind of this is what is called a smooth grad. And you see it kind of helps a little bit in kind of removing the noisiness of the vanilla gradient. So sort of like in math, you have this sample S. So these are all of the points that you sampled from a neighborhood around X. And what you do is you just basically compute the gradient each of these points, and then you average them. And kind of you can think about this explanation in expectation, that your sample goes to infinity. So kind of like these converges to the expectation of the gradient in a neighborhood. And I tell you in a second, like how we are going to define a neighborhood around the point. But sort of like, I will talk about few gradient methods, gradient explanations throughout the talk, but this is the simplest version that I stick to for the most of this talk.
Can I ask a question, Shahin?
Yes.
In this work, do they define explanation to be the gradient of function at X, or is there like a formal definition and then they show that the gradient satisfies like?
Good. So the first one, so they're defining the explanation to just be the gradient, and sort of the way they motivate this is they're saying, hey, we can use the gradient for images to basically build this sensitivity map that says big picture are important. But that's a great question.
Okay.
And a lot of things in the explainability domain is not quite as formal as what the sort of formalism that you see in like privacy or fairness. And I guess one of the contribution of this work is just kind of like adding more kind of like theoretical perspective to this type of work.
Thanks.
Sure. So let me move on to the second class of post-hoc explanations. These are called perturbation-based explanations, and I'm just going to focus on a specific perturbation-based explanation that we call C-LIME. So LIME was developed in 2016, and the idea of LIME is no matter how complex your model is, if you zoom into every specific, like any specific like area that you want to explain, maybe you can explain that with a simple model. So in this figure, you see that the model kind of like the decision boundary is somewhat complex, but if you want to explain the point that is kind of bold with a plus, if you zoom in on the left-hand side, you can kind of see that the behavior of the model around that point is roughly linear. So you can basically use that linear model to give the explanation. And in particular, it doesn't really need to be any linear model. It can be any simple function. So you can basically explain the decision of the function at any given point by just building a simple model in the neighborhood around it. And then you can basically do a lot of things to improve this explanation. For example, if your model is high dimensional, then you can do some sort of regularization to just pick the most kind of like reduce the dimension. So this is the idea of LIME. We're looking at a variant of LIME that we proposed, and we call it C-LIME. So there are some differences between C-LIME and LIME. So C is for continuous. So the model that we're going to use is just a linear model. And then we're assuming that the features are continuous, and this is an assumption that we need. And we're also assuming that there is no regularization. So in some sense, if you want to kind of get a sparse explanation, this is not what C-LIME is going to give you, but you can basically get this from LIME. But this is a specific version of Lime that we're going to focus on for this work. Okay. So again, similar to smoothgrad, you can get a sample around the point X that you want to explain. And then basically, you can solve a regression problem with the samples that you have. So if G is the class of our linear models, sorry about the typo, you can basically solve this regression problem on your sample to get the weights of the linear model. Okay, and then you use the weights as your explanation to just kind of highlight that in this specific examples, maybe the kind of weights that are high contributes more to your prediction. So you can kind of like look at the weights and see which features are more important. Okay, and then similar to the smoothgrad, we can write this as kind of like an expectation as the sample size gets large. Okay. So let me jump into the first sort of like result that I'm going to present. And for the results in this part, I need just one assumption. And the assumption is to generate the neighborhood around X that we're going to sample. We're assuming that we have a distribution P that generates a sample, and this distribution is just Gaussian, that is centered at X and has some covariance matrix. And then for the most part, we're assuming that this covariance matrix is diagonal. But I tell you in any specific result whether we use the second assumption or not. Okay. So the first result that I'm going to show you basically says that if you sample from this Gaussian distribution where the covariance matrix is just invertible, it doesn't need to be diagonal, and you look at the expected output of C-line and the expected output of a smoothgrad for any model that is continuous and for any point, these two explanations are the same. And they are in fact the inverse of the covariance matrix that you use for sampling times this vector that is basically each entry in this vector is the covariance between the ice entry of your sample point and the label for that point. So basically you can kind of think about the second one says how important each feature is, or in terms of like how much they correspond to the outputs, like what is the covariance of every specific feature. And okay.
And what is sigma in a smoothgrad?
Good. Sorry, I should have defined this notation a little bit better. So if you go back to sort of like smoothgrad, so samples for the expectation version, the distribution is from the samples are generated from some distribution P, and we're assuming that P is Gaussian with that is centered around X with variance with covariance matrix sigma. So we're just going to use sigma to say that this is generated from that specific distribution. So for the rest of this talk, you just see that this P is going to be replaced with sigma.
I see. Okay. And you assume that sigma is known?
Yes. Yes, so sigma is our parameter that we decide how to generate samples. So sigma is a parameter you can basically set. Okay, so I'm not going to prove this result, but for the smoothgrad part, kind of like we went and derived this specific closed form for each of them separately. And for a smoothgrad, we use the multivariate version of this Stein lemma. And for C-Lime, this is just kind of like you can write down the first order condition for the optimization problem that C-Lime is solved. Okay. So this was about the equivalence of these two approaches. The second thing that you might want from your explanation is something that I'm just going to call robustness. So the intuition here is if you have two nearby points and your model predicted similarly in these two nearby points, you want your explanations to be roughly similar for these two nearby points. In practice, explanations are often very sensitive to the choice of to the choice of the points that you want to explain. But what we show is like, it is indeed the case that both C-Lime and smoothgrad provide explanations that are robust. So kind of like to formalize things a little bit, the notion of like closeness that we use is the typical Lipschitz continuity. So you can kind of see the output of smoothgrad and C-Lime as a vector, and we want to show that this output is actually Lipschitz. So again, I'm not going to prove this result, but suppose the function, in addition to having a continuous feature and like mapping to the subset of reals, is also have bounded gradients. And this specific result holds for the case that the covariance matrix is diagonal. So what we show is both C-Lime and smoothgrad in expectations are Lipschitz, with the L constant being the maximum gradient of the function f divided by sigma. And this result doesn't really depend on the dimension of the explanation. Are there questions? I think it's a good point to pause for a second.
So for smoothgrad, the explanation is just a gradient of the point, right? So if your function is smooth with parameter L, it's L lip, yeah, the explanations are going to be L Lipschitz.
Yeah.
So why do we need the assumption on sigma here?
Because so the assumption for sigma, so this is the upper bound on the Lipschitz constant that we prove. It might be that it doesn't depend on sigma.
Oh, okay. Like you set L to be the maximum over to
exactly. So this is an upper bound on the Lipschitz constant.
I see.
Okay. So far I just talked about a smoothgrad and C-Lime in expectation when you had a very, very large sample. But in practice, you run these things using a finite sample, and the explainability community is kind of not as theoretically focused as like other communities like fairness or privacy. Sort of one issue that happens in practice is people run these algorithms with different number of perturbations or different number of gradient calculations, and they get different answers. So what we want to provide is basically how many samples from this Gaussian distribution you need so that your explanation gets epsilon close to the expectation. So this is the question that we want to answer. So let me first start with the smoothgrad. So this is kind of like a wall of text, but if you look at the last line, it says, look at the explanation provided by a smoothgrad with n sample, and look at the explanation that you get in expectation if n is infinite, and we want to bound the L2 difference between these two explanations by epsilon. And it says you need sample complexity that is 1 over epsilon squared. It also depends quadratically with the gradient, the maximum gradient that the function f can take, and it has the typical log dimension over the confidence parameter dependency. And this is just proved by using a Chernoff bound. So there is nothing fancy going on here. Kind of more interesting is for C-Lime. So again, we want to bound the expectation of C-Lime in expectation versus expectation of C-Lime using n samples. And we want this difference to be epsilon. So sort of like you again have the 1 over epsilon squared dependency. This is kind of like hard to read. I'll parse to it in a second. You will still have the log dimension over failure probability dependency. Here you have an additional factor of d compared to the previous bound. But what is kind of like confusing about this bound is, in addition to the dependence on 1 over epsilon squared, you have dependence on sigma. Remember, your covariance matrix was diagonal, and you have also dependence on the norm 2 of the point x, where you want to give explanation. So sort of like This result says your bound basically quadratically goes up, either if the point you want to explain has a small norm or a large norm, and either if your sigma parameter is small or large. So kind of like counterintuitive, and I think this is just an artifact of our kind of like analysis. But sort of like intuitively, you want less sample if sigma is smaller, because you're basically sampling from a point that has from a distribution that has less variance, so you should converge faster. I don't have quite a good sense of what should be the correct dependence on the size of X, but for sigma, it seems like intuitively you want a smaller sigma to result in less sample. And this is sort of like what we see in practice, that you converge faster with the smaller number of samples if your sigma is small. Okay. So this is the first part of the talk that I want to talk about unification and robustness of C-Lime and SmoothGrad. I think it's a good point to take some questions if there are any questions. Okay, so let me jump into the last part of the talk, which is about the disagreement. So far we see that explanations that are provided by C-Lime and SmoothGrad are the same, at least in expectation. But generally what happens in practice is if you have a model that you want to explain in a specific input and you use two different sort of explanation methods, they give you drastically different explanation. So this is what we want to call the disagreement problem. Our goal is to just sort of like kind of formalize what does explanation disagreement means, how can we measure disagreement, and kind of like look at kind of more practical side and see these people who use these explanations in their day-to-day life, how do they deal with this disagreement and how do they resolve? So in the first part, we want to think about what constitutes as a disagreement between two explanations, given that they're explaining the same model on the same input. So to do this, we basically run some behavioral experiments. We conducted 30-minute long interviews with 25 data scientists that they work in tech and finance. Most of these people have 2 years of experience working with these explainability techniques, and every one of them had at least 8 months of experience working with these tools. And they all use Lime, SHAP, and gradients, some of the explainability techniques that I'm going to briefly mention throughout this talk. So based on these interviews, we found out that 84% of these 25 people think that two explanations are different if the top features that they kind of pick are different. So kind of like you want to at least have explanations that kind of agree on what are the top kind of features that contribute to the prediction. 76% thinks that the direction of the feature contribution is different, and that causes the explanation to be different. So for example, each of the features can contribute either positively or negatively to the prediction. So kind of direction implies whether the feature contributes positively or negatively. So these people think the explanations are different if the direction of feature contribution is different. 72% of people thought that explanations are different if the ordering among the top features are different. So kind of like not only they want the top features to be the same, they want them to have the same order in the explanation. And 64% thought that the relative ordering of certain features is different, and that causes the explanation to be different. So sort of like in specific domains, you as a data scientist might kind of just care about how does this specific feature or this subset of specific features contribute to your model prediction. So kind of like in that subset, people were thinking that two explanations are different if the relative ordering of the importance of these features within that subset is different. And kind of like somewhat surprisingly, no one of these people mentioned that the values that these explanation methods kind of assign to each feature are different, and that causes the explanation to be different, because I think there was a general understanding that these are different techniques. They kind of like compute the importance of each feature in a different way and in using a different scale. So kind of like nobody really looked at the exact value that these features, these methods assign to any specific feature. Okay. So using these insights from the interviews, we designed 6 metrics to compute how different 2 explanations going to be. So the first one is called feature agreement. So basically, if you're looking at the top K feature, K is your parameter, what fraction of those top K features are in common? You can kind of make this more restrictive. So in rank agreement, not only consider the features to be the same in the top K, but they also take ranking of those features into account. Sign agreement, instead of taking the ranks, take the sign into account. So features should be the same and should have the same sign. And then you can have the most restrictive one of these that's called sign rank agreement. So features should be the same, they should have the same rank, and they should have the same sign. So this is for the setting that we pick the top K feature. There might be settings that user specifies a set of features that they are interested in. And sort of like we want to come up with a metric that says how different 2 explanations are. So the first metric that we define is called rank correlation. So this is just the Spearman rank correlation between the features in the set F. And then the other metric is called pairwise rank agreement. So we look at any pair of features in the set F, and we see that whether the explanation give the same relative ordering of importance between these pair of features or not, and we just kind of average that over all pairs of features. Okay, so these are the 6 metrics that we define to measure the disagreement of 2 explanations. So our next question is, we want to know in practice, like how much explanation disagree across different sort of data sets and different sort of models. So we looked at tabular data, text, and image data. So just kind of like dive in a little bit more to our setting. So we have data sets from 3 different data modalities. So we have tabular data. For tabular data, we have the COMPAS dataset and German credit dataset. And we have a vision dataset that is ImageNet, and we have a text dataset that is some corpus of news. And for each of these datasets, the model that we use varies. So for the text data, we train 4 models: logistic regression, gradient boosted tree, random forest, and neural network. For the vision dataset, we trained ResNet 18. And for the text dataset, we trained a model using LSTM. So these are the black box model F that kind of like we want to explain. And for explainability techniques, we use 6 different post-hoc explanations. I talked about Lime earlier, and also gradient in smoothgrad. Another perturbation method is based on Shapley value, and we use a specific instance of that called kernel Shap. So kernel Shap and Lime are the perturbation-based techniques. The other 4 are gradient-based. So I told you about gradient in the smoothgrad. Gradient times input is just very simple. You take the gradient and you also multiply that by the input point. Integrated gradient is a little bit more complex, but all you need to know for the rest of this talk is 4 of these are gradient-based and 2 of these are perturbation-based, and these are the most common post-hoc explanation methods that people use. Okay, so I'm just going to show you the result of the explanation disagreement on the COMPAS dataset. For this talk, we observed similar observation when we looked at our vision dataset and when we look at our text dataset. So remember, the way I define disagreement measures, you need to pick the set of top K features. So for the COMPAS dataset, there are 7 features, and we pick K to be 5. So we look at the top 5 features selected by the explanation. And we basically compute explanation over a set of point X. We compute the disagreement for any any two explanations at that specific point, and we average them out over all of the points that we try to explain. And
can I ask a question?
yes.
So these explanations give you a single number, right? The app, or like, oh no, they could be vectors.
So explanations can be vectors.
Okay.
So the measures that I introduce kind of like takes two vectors as input and convert them to a number that is like how different they are. So here we're looking at the data set, and we want to explain every point in the data set. So I can compute the disagreement of the two methods on every single point in the data set and just average them.
My question was, how do you find the top 5 features? What do you mean by top 5?
Okay, good. So basically, all of these features assign numeric scores to features. So top 5 means the 5 features that have the highest numeric scores in absolute value. So kind of your explanation, if you want to think about it this way, it says, how important is this feature? I'm going to give it a number. That number can be positive or negative. So the top 5 features are the features with the highest score by your explanation.
So in the case of a smooth grad or gradient, you have the gradient as your explanation. You look at the top 5 in terms of magnitude, and then the corresponding features are the top 5 features.
Yes. Sure. And for this talk, I'm just going to talk about the neural network model that we train on the COMPAS dataset. We get similar results with other models. And this neural model is pretty accurate. It has error less than 1%. Okay, so there is a lot in this figure. So let me walk you through it. So each of these subfigures correspond to a different metric that we had to measuring disagreement. There were 6 of those metrics. So there are 6 figures. In each figure, kind of each entry says what is the disagreement, what is the agreement between every pair, one on the column and one on the row. So kind of the diagonal is always 1 because it's the same method compared with each other. So they agree 100%. Colors mean red, like more darker means more agreement. And the brighter it becomes, it means less agreement. So kind of like, I don't want to walk you through all of the details are here, but you see a lot of kind of entries with bright color. That means the agreement is very, very low. So at least kind of like we see a lot of disagreement when we are trying to kind of explain the decision of this neural network model on the COMPAS dataset measured by sort of like different metrics that we design. So that's the takeaway that I want you to take, that it kind of like in all of the data sets that we looked at, in all of the models that we looked at, we saw a lot of disagreement between the explanations. And kind of like the higher level takeouts that I want you to have is kind of like consistently as K, the set of top features increase, the rank agreement or the sign rank agreement decreases. And this not only happened for the neural network, it happened for the logistic regression, it happened for the other 2 models that we trained. Kind of the interesting observation here was that among the 4 gradient-based approach, it seems like gradient and the smooth grad consistently agree with each other, while at the same time, integrated gradient and gradient times input, sorry for the typo, consistently disagree. So there seemed to be kind of like a dichotomy among the gradient-based methods in terms of like which one of them agree with each other and which one. And these patterns also happened in the other data set. Remember, I just talked about the COMPAS data set, but this also happened in the German credit data set, and even there were more disagreement in the German credit data set compared to COMPAS. And kind of like, interestingly, the disagreement in both of these data sets increased as we make the model more complex. So the neural network had the most disagreement between the explanations, and the logistic regression had the least. And I'm not going to talk about the vision data set and the text data set, but we sort of like got very consistent results on those data sets as well. Okay. So we sort of like design these metrics that tells us how different explanations are. And we saw that in kind of like a lot of domains, these metrics show that the explanations disagree a lot. But the next thing we want to kind of figure out is, do people who use these tools, do practitioners who work with these explanatory techniques kind of like also experience these disagreements in their day-to-day life when they're using this tool? And sort of like more importantly, if there is a disagreement between the two types of explanation they get, how do they approach this? How do they resolve this agreement? Which one of these kind of like explanations they go with? So we did an experimental setup that I think it's much easier to explain with a figure, as I'm going to do next. So we looked at explanation generated for the COMPAS dataset. So again, there are 7 features, and we kind of told them what is the COMPAS risk score prediction task. So what are the features? What are you going to kind of predict? What model you use? And sort of like all of these people know about explanation, but we also told them what are these 6 different explanation metrics that you are going to compare. And we gave each of these people, I think, 15 prompts. And a prompt looked like this. So there are 2 explanations. So here, for example, you see an explanation provided by Lime. And on the right side, you see an explanation provided by the gradient input. So each explanation, basically, there are 7 features. Each explanation tells you how important each feature is. And kind of like it also has a different magnitude of how important. So for example, age with the left model has like 0.1 positive correlation, and race has minus 0.05 in the explanation. So sort of like we give them pictures like this. I say, here is a explanation by Lime, here is a explanation by gradient times input. And the question that we ask is, do you think these explanations mostly disagree, or completely disagree? And we ask them to explain the result. And then the next question we ask them is, which one of these explanations you think is the right explanation, and why? And then at the end, when they answer these prompts, we ask them several different questions as a questionnaire that I get back to those at the end. So sort of like here is what one prompt looked like. It's everything that I showed you in one figure. So you have 2 explanations, whether they agree or disagree as a question, and which explanation do you prefer or rely on? Okay. So then after they finish doing these 15 prompts, we ask them a set of questions at the end of the experiment. We ask them whether they have used the explainability methods before, what do you use these methods for, what data modalities do you use when you're trying to create explanation, which of these techniques do you use in your day-to-day life, which of these techniques do you prefer, and sort of like how do you resolve disagreement in your day-to-day life? And we're going to see their answers to all of these questions. So let me talk about our findings. So we had, again, 25 participants. These 25 participants are different from the first experiments that I talked about. 13 of these participants are from academia and 12 are from industry. The academia participants are graduate students and postdocs, and the industry participants are either data scientists or machine learning engineers from 3 different firms. I think 2 of them are in general tech and 1 in finance. And out of these 25 people, 20 of them have used explanatory techniques before, either to do research or kind of debug their model, or in terms of the industry participants to help client explain the model. So in particular, in our analysis, we are interested in 4 questions. One is, do practitioners observe disagreements in the prompts that we give them? And if so, are there any explanation that is preferred over the other ones? And sort of like, if there is a disagreement, how do they resolve this disagreement? And in particular, how do they resolve disagreements in their day-to-day life when they're using these tools? So the first question, that whether they think that explanations generated by these 6 techniques in the prompts that we show them are different or not, 68% of the participant, 68% of the prompt were marked with completely disagree or mostly disagree. So a lot of them are that not only are kind of metric, measure them as disagreement, but also these data scientists that just look at the explanation think that they disagree. So the next question we want to think about is like, in case there's a disagreement, which one of these techniques are favored by the people? So in this graph, you see on the kind of like y-axis a pair of explanation, and kind of the bar tells you if there is a pair of explanation, whether the left one is preferred, the right one is preferred, or neither of them are preferred. So you see a great degree of sort of like variability in what people kind of like prefer. So for example, if you look at the 5th line from the bottom, roughly like 40% of the people prefer lime, roughly like 40% prefer gradient, and 20% prefer neither. So there is a large degree of variability in what explanatory technique they think is make more sense. And in particular, gradient times input was surprisingly favored the least, and SHAP at 7%, and SHAP was favored the most at 67% of the prompt that involved SHAPs. So that was kind of an interesting result. And from sort of our questions about why do you prefer the explanation, we got the sense that people preferred SHAP because this is tabular data. And remember, the sort of like the way I motivated the gradient-based methods was using them to explain images. So it seems like people generally agree with the sort of like that high level intuition that gradient-based methods are better for images. So when you're using tabular data, they prefer something that is perturbation-based. 25% said they're more familiar with SHAP. And sort of like, interestingly, SHAP is the only one of these approaches that have some sort of like theoretical analysis and some theory behind it. So 14% of the people thought SHAP is better because it's a better and more rigorous algorithm overall. So the next thing we want to kind of measure is how do practitioners resolve the disagreement? So we found out that 33% think that one method is better than the other because it has some theory. 23% said they think one method is better because the explanation they generated kind of matches their intuition better. And as I said in the previous slide, 23% of the people were generally in favor of Lyman SHAP in our experiments because these are perturbation-based methods, and they think for tabular data, you shouldn't use gradient-based methods. Okay, so the last thing I want to cover is we then at the end of the survey, we asked them, how do you resolve disagreement in your day-to-day life? And kind of like the answers we got are very interesting. So 50% of the people who observed this disagreement in our experiment, they said at the end of the day, they just make arbitrary decisions. 36%, they said they're unsure or they don't know how to resolve this. And interestingly, only a very small subset of these people said they look at other metrics like fidelity of the explanation. So you kind of think about fidelity as measure of like what would be the kind of like how much your explanation is kind of like faithful to the model that you're trying to explain. And you can come up with metrics to measure that like fidelity, but it turns out that most people just make arbitrary decisions when they try to resolve disagreement, which we found to be kind of interesting. So this is all I have to talk about. Just to summarize, we look at explanations that are generated from either perturbation-based method or gradient-based method. And in particular, we show C-line from the perturbation side and the smooth grad from the gradient side are equal. In practice, explanations disagree. And we sort of like presented a framework that lets us measure the amount of disagreement between two different explanations. And then quantitatively, we found that explanations disagree in a variety of settings, and we sort of like confirmed many of our kind of results on using human subject experiments. So I guess that's all I have to talk today. So happy to take questions. Stop sharing.
Well, thank you, Shahin.
Sure.
I
Yeah,
have a question.
Oh, do you want to go first?
for it.
Sure. Actually, would you mind just going back a few slides? I had a question on when you were explaining kind of like the breakdown of not disagreements, but like how I think maybe slide 51, was it 51? Yes. I think this one and maybe the one before, and like, but yeah, basically when people like talk about this disagreements and everything, you have those numbers that are across like 25 people. Do you have an understanding of the breakdown between kind of like industry practitioners and academics? Because I might imagine that it might have different reasons for which they like or don't like an algorithm as a function of like, you know, what they do.
I don't have the breakdown off the top of my head, but it might be in the paper.
Okay. Do you remember at a high level if there was a difference or not?
I don't think there was a difference between these sets. Yeah.
Yeah, I was gonna ask, can we look at explaining the model itself instead of explaining the predictions given by the model? For example, we have a model with like parameters. Can we explain what these numbers for parameters mean?
Good question. So generally, my understanding is the sort of explainability literature falls into two categories. One is these post-hoc explanations. The other category is they're trying to build simpler and more interpretable model and kind of like how to optimize for that. They're just like work that people basically try to kind of take a global view and kind of build models that are explainable themselves. So either models that are sort of sparse by nature or sort of like the models that uses a few decision rules. I think one of my co-authors, Hima, has a lot of work on, I think it's called decision sets. The sort of like, how do you basically build a model that is simple and interpretable for human, and just kind of like, instead of building a complex model and try to explain it, why don't you build like something more explainable itself?
And are interpretability and explainability the same thing in this? Are they the same field, or are they like different in nature?
They are the same thing, but I think most of the people just work on post-hoc explanations because you can't really like build a simple model without sacrificing a lot of performance in many of the settings. So there is really not a whole lot of attention on building global explanations.
And a more like fundamental question: why should we care about explainability if like we have an accurate model that makes perfect prediction? You know, like why should we?
Yeah, good. So kind of like explainability comes into the picture when sort of like these tools are used by humans who want to trust them. So for example, in the example that I showed you with the doctor, why should doctor basically trust a model's prediction that says this person has flu. So sort of like one way of thinking about why explanations are useful, it can sort of like help us trust the model. It can help us like debug the model. So one way of kind of debugging is if your model is basically kind of discriminate against a specific population, even though you don't really like feed in information about like race or sex to your model. But when you do the explanation, you kind of see that the model is basically using zip code as one of the important features. So kind of like you can use the explanations to debug the model and just kind of like measure things like discrimination in the model. So there are a lot of like useful ways that you can use these explanations.
Thank you.
Sure.
Yeah, I think like from a behavioral point of view, right, it's super important to say if you're going to deploy this in like a high stakes setting, like, yeah, I don't know, medicine. It's like, yeah, why is this model reasonable? And like, why is this something human beings should trust? And I'm guessing if you deploy like a super complex neural net, but you don't have an explanation of like why it does at a high level, then people are just gonna be like, that seems like a very weird thing to do. It's a black box. Why should I trust this thing over my, I don't know, doctor? But, you know. Anyway, do you have any more questions? Because if not, it's almost 1 p.m. So happy to call it a day.